Everyone. Okay. Sorry. Yeah. All right. Welcome, everyone. Thank you for coming to this talk. It's hosted by the Center for Advanced Mathematical Sciences. I'd like to thank for hosting Professor Anand Sarwate. So Professor Anand did his PhD in Berkeley, California, and then he did his postdoc at UCSD. Then he was an assistant professor at IIT Chicago, and he's currently an associate professor at Rutgers University. And he has a very wide range of interests. So he has a background in information theory. He's also worked in optimization and privacy and security, and of course in machine learning. But what's not in his bio that he's also done theater. So really could talk to him about anything. He's also been named a distinguished lecturer of the Information Theory Society. So really looking forward to his talk, which will be about structured tensor decompositions. And, help me welcome him, and I'll leave the floor to Anand. Thank you.
So thank you all for coming. So yes, I'm here, as a representative of Rutgers, but also the Information Theory Society. It's weird. I work on privacy, so I should be indistinguishable, but they decided to reduce my privacy by calling me distinguished. I'm not so distinguished. But so I'm going to talk today about some work that I've done in the last few years on trying to understand how to work with tensor structured data. And so I'll try to explain what I mean by that, because the word tensor is kind of overloaded, or rather people come at it from different perspectives. And so this is joint work with my colleague Wahid Bajwa, and the most of the work I'm going to talk about is with his student who's about to graduate. In fact, I got the invitation for her PhD defense like yesterday, Batul Taki, and then two previous students, Zara and Mohsen, and then an undergraduate who came to work with me last summer, Jose Hoya Sanchez from the University of Central Florida. And the work, I have to thank everybody who pays for things, right? So thank you, the National Science Foundation of the US. Thank you for the National Institutes of Health. And again, also thank you to the IEEE Information Theory Society. So let's talk about tensors. So how many of you know what a tensor is? Or think you know what a tensor is? Or have heard the word tensor? Certainly you've heard the word being tense, so that's good. So let's try to be more relaxed. All right, so what's the history of the word tensor, right? So it's actually, this is a kind of interesting historical anecdote. So, we can go to look at the physicists, and I know there are a lot of people with physics background here. So here's, maybe your favorite physicist, Hamilton. So he used the word tensor to mean actually the norm of a quaternion. And so his tensor is actually a scalar, and we're thinking what we're going to talk about is tensors are multidimensional. So this is not the tensor that we're going to be looking at. So apologies to the physicists, no more Hamilton. There'll be more physicists later. There's another physicist, Voldemar Voigt, who I think was maybe the first instance of the use word tensor in German, of course. And then kind of things kicked off from the mathematical end of things with Gregorio Ricci Curbastro, who developed this theory of tensors. Apparently, it was really great work, but it was very hard to understand for many people. So he had a student, Tullio Levi-Civita, who wrote a book on it with Ricci Curbastro to explain this kind of tensor calculus to people. And so here's Ricci. So this, for the students in the audience, if your advisor is really hard to understand, you can become famous. Levi-Civita is not very famous by explaining what it is, whatever it is that your advisor is not capable of explaining clearly. So from then on, we have a series of developments. Albert Einstein appears in the picture, so that's great. So the physicists should be happy again. So Einstein and Grossman, who maybe is less well known than Einstein, used this tensor calculus to essentially the underpinnings of general relativity are written in terms of tensor calculus. Now to dig at the physicists, apparently they didn't quite use it correctly. So Levi-Civita and Einstein had a very long correspondence, multi-year correspondence, where Levi-Civita tried to fix the actual math in the theory. to make it more rigorous. And it was very friendly, unlike kind of the review process these days. This was a very friendly correspondence. So this is the ideal of maybe what scientific exchange should be. And then in English, the first really use of the word tensor was in a book by Hermann Weyl. So, and this uses the word tensor analysis, and this kind of is where things kick off. So from this history, you can see that this use of the word tensor is really coming out of the physics literature. So what is a tensor, right? So it means, the word tensor means very different things to different people. And if you're a physicist, maybe you think about it in one way. And if you're a signal processing person or an electrical engineer like me, you think about it differently. We're going to think of them very mechanically, I call it mechanically, not mechanical engineering, but mechanically, as a multidimensional array. So I'm just going to think of it as a data structure that is a multidimensional array. Right, so a first order tensor then is a vector. Second order tensor is a matrix, so it's 2 dimensions. So order is the number of dimensions of my array. And the third order tensor is this, cube-like object or some rectangular solid. So a tensor in general, with a kth order tensor, is just going to be an object, a multidimensional array of real numbers. You could also think of complex numbers or finite fields or whatever you want. We're going to stick with real numbers. But there are actually other perspectives that I think are important to know about, that maybe are less programming friendly. One is to think of a tensor actually as a point in the tensor product of vector spaces. And so this is a more geometric view of a tensor. This is, in a sense, basis independent. You don't need to have a basis for these vector spaces specified. Whereas when you write it down as an array, that's choosing a particular basis for each of these vector spaces, then you can write it as this multidimensional array. So this thinking of it as a point in this tensor product of vector spaces allows it to be basis independent and gives you kind of a more geometric view. Another way in which this representation, if you like, of this tensor object is if you think of a multilinear operator. You can write it down as a multidimensional array. In particular, these are called tensor representations of the general linear group. So this is a connection to group theory and representation theory. So where do we see tensors? They really appear everywhere if you're coming at it from engineering applications. So you see them in medicine, for example, in neuroimaging. A magnetic resonance image, MRI, is like a 3D brain scan, so that's a 3D object. You also get them in other types of medical imaging here as well. In geosensing, you see them in hyperspectral imaging, where you have 2 spatial dimensions, and then at each pixel in this image, you're actually collecting not just RGB, but a whole spectrum of values. In communications theory, you can see them in multi-antenna systems where you have multiple antennas at a transmitter communicating to multiple antennas at a receiver. And there you can look at so you can see here it looks like it's 2D because it's there's a graph, but you can make it higher dimensional if you consider delay and Doppler shift and so on. So you get these multi-dimensional arrays also that you might, for example, want to estimate in the communication system. You could just think abstractly, I have a box of numbers, and then you impose some constraints. You could take a joint probability mass function on multiple variables. Also, you can write it as a multidimensional array, and then you can ask questions about the structure of that array. In network science, you can think of a time-varying graph. I have the adjacency matrix of a graph, and I look at it over time, and then over time, it starts to look like another 3D object. And there are many other applications for this kind of processing and chemometrics, numerical linear algebra. Many of the things that we'll talk, the factorization structures that I'm going to talk about today, came up in the context of psychometrics, and also their connections used in theoretical computer science. So what do we want to do with tensor data, right? So we want to do basically all the things we'd like to do with vectors and matrices, same, except now we have multiple dimensions and it's harder to draw. So things that we might want to do are things like signal recovery. So in signal recovery, for example, I have an object and I have a sensor. I take an image of the object, like a brain scan, right? And then I'd like to produce the scan, right? So that's signal recovery. In terms of machine learning, you also might want to think about unsupervised learning. So in unsupervised learning, you have a bunch of measurements that you've taken, tensor valued measurements that you've taken, and you'd like to find a basis or some way of representing them, extract features from them such that they end up being clustered in some way. You could also ask about supervised learning. So maybe I have them already like this, and I'd like to find a rule that can tell, for example, healthy brains from diseased brains, right? And as a concrete example of this, I was just in Greece, and there was a question like, who makes the best baklava, right? And so obviously there are the diseased brains, and then here are the healthy brains, right? So we're playing to the home team here. And then you also have data compression, right? In data compression, you might want to take a large signal, and you might want to squish the brain into a smaller brain, right? So these are all the types of things in machine learning or signal processing that we would like to do with this kind of data. So what's an example of an unsupervised learning problem with tensors? By the way, before I continue, please stop me and ask questions if anything is not clear. I'm happy to, it's better to go through less material, but have people understand than to go through more material and have people not understand. So the problem in the unsupervised learning problem that we've looked at a bit is something called dictionary learning. And in dictionary learning, the idea is you have a collection of data. So I have a collection of tensor valued data, so a bunch of brain scans, for example. What I want to do is find a way of describing all of this data, and then hopefully future data, using only a small number of words, or if you like, dictionary elements. So they call atoms that are called in dictionary learning. But so I want to have a dictionary also of tensors, such that each of these y's can be written as a linear combination of these dictionary elements, but most of them are zero. So the only s of them are non-zero, for example. That's that would be the dictionary learning problem. And so the application here would be, for example, if I have a drone and it's acquiring images, if I represent the images just using these coefficients, it'll be a much smaller storage and also much less to communicate than if I have to send the whole multidimensional image directly. So this is a way of doing data compression. So supervised learning problem, we're just going to look at the, we call it learning. So, when I was in school, this was just statistics, regression. So statistics, but now we call it learning because it's more fun, right? So we have a collection of labeled data now. We have a tensor and a scalar response. So it might be, again, if we think about the neuroimaging context, it could be the brain scan and then some property. One thing that people are interested in neuroscience is, given a scan of the brain, can you tell how old the person is? So you want to predict the age of somebody based on the brain scan to see, and then you can then go back and say, like, well, what parts of the brain are associated with aging? So we want to find a regression tensor such that if I take essentially the dot product of these two arrays, that's approximately what the response is. So the age is approximately the dot product, some linear combination of the entries of this of the x, the image. This is the element-wise inner product. And so again, you might want to predict age or brain health from an MRI, right? So something like this for a classification problem. So if you wanted, yeah. So what do people do typically with this kind of data? And historically, people would essentially take the 3D data, and if you download a package, or if you work with some of the basic Python packages, what it'll do is it'll take the multidimensional array, it'll reshape it into a gigantic vector, and then it will just plug it into whatever existing function it has. Right? So what does that look like? If I have an image, for example, which has 100 by 50 by 110, then I'm going to have to learn in my regression problem, I'm going to have to figure out 550,000 coefficients in order to predict something about this image, a scalar response to this image. So from a statistical point of view, it seemed like you would require a lot of data to be able to fit this many parameters. So the question is, can we reduce the complexity one question is, can we reduce the complexity? And the other is, can we not, this vectorization kind of destroys some structure that we might have, right? So here's the problem with vectorization. It ignores this tensor structure. So there might be, it seems pretty reasonable to assume, especially in imaging contexts, that nearby pixels or nearby entries should be potentially related to each other. But if I vectorize, then I sort of ignore that information. I have to sort of rediscover that they are in fact related to each other, just purely through correlations. The second problem is computational, and since the resulting problems have very high dimension, we don't have enough statistical power to do this. And so this ADHD 200 data set has scans of children's brains and whether or not they're diagnosed with attention deficit hyperactivity disorder. And so these are the size of the tensors, and so we end up with a 2 million dimensional problem. Unfortunately, the sample size for this data set is less than 1,000 images. So the problems I'm interested in are in situations where you actually have very low number of samples because they're expensive to collect. MRIs are very expensive to collect. I don't know what the current price is, and also the prices vary from location to location, but it's very hard to get, it's very expensive to collect this much data even. So of course, overparameterization is not or the lack of small sample size is not just a problem with tensors. This is, of course, deep learning is supposed to solve this for us. But this is actually in a pretty extreme setting where you have very few samples. And so it makes sense, I would like to argue at least, it makes sense to make the model that we use at least smaller, or at least something that we can scale to the amount of data that we have. That is, we can reduce the number of parameters. If we get more data, we can expand the number of parameters to fit that model. So if I have a regression model like this, where my response is dot product plus noise. If it's a vector, if I think of the x as a vector, it's a 1D tensor, then a typical assumption is that people will model this as sparse. So it's a little bit hard to tell with the color, but I've made some of the boxes white to say that those are zeros, right? And so if I make the assumption that only a small number of entries of this vector are responsible for this response, then the number of possible values for V is reduced. The structure, there's a lot of structure in the V. So that's what you do for 1D. For 2D, you model it as low rank usually. So you'll take this matrix and you'll say it has low rank, therefore it can be factorized. And because it can be factorized, we have to learn these factors, and the factors contain much fewer parameters than the original matrix. And so the question is, how do you impose structure on tensors? I'm not inventing this idea of imposing structure on tensors. I'd like to describe the ways in which people impose structure on tensors. So what I want to talk about is what are called tensor decompositions. And then I'd like to talk about this regression problem that I mentioned as a motivation, and talk about what we can say about tensor decompositions in that setting. In particular, I'm going to introduce a new tensor decomposition, or a special case of an existing very general tensor decomposition, which we found to be very useful in a number of applications. And time permitting, I'll talk about dictionary learning with these structured tensors, and then I'll hopefully conclude with some pointers to some future directions. Maybe you would be interested in working on some of these directions. So, questions? Good time to stop. Red slide. Good time to stop. Yeah, everybody good? Okay. Okay. Unfortunately, you go and you. So you go and you say, I'd like to learn about tensors, and then I hand every student, I say, take this paper by Kolda. You can't really see the hands. Kolda and Bader from 2009. It's a SciAm review paper. I say, go read this paper. And then they immediately become like overwhelmed by the notation and like all of the terminology. So I'm going to try to limit what we need to use for this talk, but I have to do something. So I apologize. So what are the two concepts that we're going to need? I'll introduce them slowly. One is we saw the order of a tensor before. It's the number of dimensions. So that's fine. Order of the tensor is the number of dimensions. And the mode refers to which dimensions. So mode 1, mode 2, mode 3. So that's good. So let's look just so we're on the same page. If I had this hyperspectral image, right? Mode one in this case is this vertical thing. It's the spectrum. So this is energy, you know, like strength at different frequency values. And mode 2 and 3 are the spatial dimensions, latitude and longitude, if you like, of the image. All right. So the next thing I'm going to need is how do you multiply a matrix and a tensor? And if anybody in the room is interested in high performance computing or numerical computing, this is actually also a thing that people are interested in high performance computing. So I can take a tensor G and I can multiply it along one of the modes, say along mode K. So I can take G and I can multiply it by a matrix. And what I'll do is I'll take the previous dimension of G, say, which is Rk in the kth mode, and I'll change it to Mk by multiplying by this matrix. Right, so how does that work? So if I take this and multiply this tensor with this matrix P1 along mode 1, then what I'm going to do operationally is I'm going to take along mode 1, I'm going to write this G as a sequence of vectors, and I'm going to multiply each of these vectors by this matrix. And that's going to then transform all of these, and then I'll stick them back together. So imagine I take I take the cube and I slice it into French fries or something, frites, I guess, and then I expand or bite some of the frites, right, and then I put them back together. Yeah.
So BK is RK by MK.
BK is RK, MK by RK. So these are RK. This is R1. And then this is M1 by R1. So then it turns into M1.
Oh.
Yeah. Yeah, you can do it slice by slice. Right. Yeah. You could do it. You could do that. I like to think of it as fibers because it's like very clear. It's just a matrix vector product, and then everything's matrix vector products, which I feel comfortable with. But yes, you can defend. You could also think about slicing and then rearranging the slices and then doing a matrix multiplication and then reassembling it. This way, I find makes it clear how you reassemble things. But good question. In fact, this intuition that you have will make it easier to understand the next thing that I talk about. So, you could write things with a left multiply as well. Canonically, people like to think about things as a right multiplication. There is a lot of stuff. These things don't commute with each other, so you have to There's a lot of this is why things get messy as you go along. Great questions. Right, so I can chain them together, right? So I could take this cube and I could, suppose I could write this bigger cube as some smaller tensor, and then I write it, I hit it with matrices along each direction to create this one. So I could either be shrinking it or expanding it. Right, and so this, you can just chain these together, and we could do them in whatever order, and we can do them in different orders. But if we write it, in order by mode, we can say X factorizes in this way. Kind of like you have a matrix can factor into the product of two matrices. You can write a tensor X as a tensor G multiplied matrix using matrix tensor products by a bunch of matrices. All right, we're almost there. Right, so let's do an example. So if I have a hyperspectral image, for example, and I want to low pass take a low pass filter, that is, keep only the low frequency components of all of at each location, I can do a mode 1 multiplication by a matrix which corresponds to taking that low pass filter. Right, and that will apply this low pass filter to every spectrum and keep only the low frequency information from the image. So it's a pretty natural process. Multiplying along mode 2 and mode 3 makes kind of less sense. Like, am I going to blur over spaces? Like, I'm moving really fast in this direction, so I blur it that way or something. It doesn't make as much sense to do. This one makes sense. So the point is, but based on the application, multiplying along different modes makes more or less sense. Okay, so the other thing you need, we need, or should maybe consider when you think about matrices, are what is the rank? What is the rank of a tensor? And so we want to get a handle on what rank is. So in 2D, if you want to write the rank of we want to write a rank 1 matrix, you just take 2 vectors and you take their outer product. That is a rank 1 matrix. So I could take 3 of them. I could write a vector, 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 this. I'm glad that I don't have a board, because if I try to draw things, it would be a disaster. So this looks maybe more reasonable. So if you can imagine B3 is going into the wall, then this is really a rank 1 tensor, right? So and we can then write one of the famous decompositions, maybe the first tensor decomposition that people look at, is something called the CP decomposition, because it was proposed by different people using confusing acronyms, and now we have short 2 letters. It's nice, CP decomposition. And so we can if we can write our overall tensor as a sum of these rank 1 tensors, R of them, then we can say like, oh, it's a representation of order R. It takes R terms to do this. And in fact, this is how you define CP rank. But so CP factorization then would correspond, if I think about my matrix tensor product now, as I can say I have all of these rank 1 outer products. What I can do is I can stick these alphas into a small tensor in the middle here, 3 by 3 tensor, or R by R tensor. Stick things only along the diagonal. And then I can write it as a mode-wise product of these using these matrices by stacking up all these rank 1 matrices. So I can write the CP decomposition as G in this matrix, this tensor with matrix products. So then now going back to the original statistical question, how many parameters do I need to fit such a model? Well, I'll need one of these for each of these coefficients, that is all the diagonal elements of this G. So that's R. And then I have for each of the modes, I'm going to get R, these vectors, so I need R, K, MK, R, MK, more parameters. And this is going to be much smaller than the product of all the MKs. So this will be a much more parsimonious or much more simple structure. And maybe I'll have enough data to fit this model. But if you look at this, you're like, well, and you're like me, and you're incapable of throwing things away. So you're a hoarder. You're like, look at all this empty space. I could put things in here. I could put things in this empty space. I'm only using the diagonal. So let's buy some more furniture or whatever and stick it in there, right? And so then you get something called the Tucker decomposition. So if I fill in that center cube, now I have this thing is not just on the diagonal, only non-zero on the diagonal. It's full up. Then I could write this factorization out, and this is what's called the Tucker decomposition. It's a little bit more complex because now you allow more interactions. So what they call this G then is a core tensor. We'll think of G as being small. And then we use these matrix tensor products to kind of blow up the small G into a big tensor. And we'll say my data looks like this, or my parameter is going to look like this. Right? The total number of parameters here now is the number of entries in this cube, which is the product of the RKs, and then the size of these matrices. So I've expanded the number of parameters, but now I can maybe describe more complex objects using more complex tensors using this factorization. So CP and Tucker, those are the two famous ones. We're on the same page so far? We're so good? Okay. So now rank. So the CP rank of a tensor is the smallest number of rank 1 tensors needed to write the tensor. And so this was actually the first reference is from 1927, and then the reference that everybody uses is from 1977, because the 1977 one is more in language that we can kind of understand. The nice thing about the CP rank is that the minimal decomposition is often unique. Often there's like a lot of technical conditions under which it is unique. And there's some necessary and sufficient conditions which are not the same. And computing the rank, though, unfortunately, or determining if the rank is R is like NP complete if the entries are over a finite field, and it's NP hard for Q, and this is done by a reduction to 3-sat in a paper by Hostad. Resolving a conjecture of Gonzalez and Jaja, this is not the politician Jaja, but actually it's his brother, who is a professor at the University of Maryland, and AUB graduate in mathematics. So, but for a local, that's a local connection. And then Salim told me that this is maybe a fraught local connection, but it's not political, it's mathematics. So that's CP rank. The Tucker rank is a vector because this cube in the middle, the G that I had before, is multidimensional. So there's actually a vector of ranks. So there's a rank vector. It's not generally unique, but we have algorithms for computing a Tucker decomposition using something called the higher order SVD. So both, if for those of who are very familiar with the singular value decomposition, the SVD, both of these are generalizations of the singular value decomposition in certain ways. The CP is the kind of the most direct generalization, and the Tucker rank could also be thought of as a generalization. So this is this higher order SVD. And there's a bunch of algorithms out there. I'm not listing all of them. But if you're interested, the survey that I mentioned will have the information on that. So this Tucker rank, unfortunately, is not unique. But as I was saying earlier when I was meeting some of the students, as in, think from an engineering perspective, you're like, okay, it's hard, but like, what can we do then? So now we're going to ask, what can we do? The last now piece, so now that we've kind of got to these decompositions, now I have to go back and introduce some more terminology. Sorry, again. So what I can do is if I take, and this goes back to your slicing question, I can take a tensor and I can take, slices along faces, 2D slices, and then I can rearrange those into a matrix, and I can do it along I can slice along any dimension. So I can slice them. These are with the fibers, but I could slice them like this, or I could slice them like this, or I could slice them like this. 2 different ways of slicing it up. Some may be more preferable than others for computational reasons. For those who like to cut onions, there's also preferential ways to cut an onion. So things can matter how you slice things. But what the nice thing is about thinking about these slices is that I can actually write this Tucker factorization. If I now say I'm going to vectorize the original, the big thing, I can write it as a matrix vector product with a vectorized version of the core tensor G. So what I do is I should have probably put the original guy, but I can take the big tensor, I can write it as a big vector. I can then write this G as a small vector. And then I can write the big vector as a matrix with certain structure on this multiplied by this small vector. And this X with a circle around it, this is the Kronecker product of matrices. And for those who you don't remember or don't know what a Kronecker product of matrices is, the Kronecker product of 2 matrices, you take one matrix and make copies of it inside the other matrix and then multiply by the entries of that matrix. So it's like so making copies inside. And so this Tucker decomposition ends up being this Kronecker product of these matrices. So now if I want to think about a statistical problem, or I want to think about an estimation problem, and I say, my tensor that I want to estimate has a Tucker structure, then it reduces to say finding these factors and this G, but then now I can kind of write it as a vectorized, I can write it as a vector problem, but not in the naive way where I just vectorize the thing and hope for the best. Here, there's a lot of structure. You can see what the structure is, saying that it's a lot of structure in this tensor. Unfortunately, I say there's a lot of structure, maybe there's too much structure. That's kind of the departing point. This is now I can talk about slightly new stuff. So there, so if you want to say, if you're like, here, I have this model, you say, I want to make, this is too restrictive. The natural thing to think about is I'll just take a bunch of them and put them together and say, I have a combination of these different things. And I can say, well, I'll take S of these and I'll just have S of these Tucker factorizations and say that my tensor now can be written as a combination of capital S of these. So this is definitely more flexible. I can just increase terms and like make it as complex as I want, but like also it's like unwieldy because I've kind of destroyed some of the structure. Question? No, so I'm basically taking this one and I'm saying, well, one of them is not enough to fit my data. What if I had a linear combination of many of them? Not just one of these. I'm basically saying, let's now say, okay, let's take many Tuckers and say it's a mixture of the Tuckers. Kind of like if you're modeling data and it's multimodal, you'd say pick a mixture of two Gaussians instead of one Gaussian. Take a mixture. That's the natural thing to do. But the problem is now, like you've lost there's no relationship between any of these terms. There's nothing tying them together. So it's it's like too much freedom. And so maybe you need a little bit less freedom. And so that's what we're proposing. We're proposing chaining, linking them by forcing them to all to use the same G, the same core tensor. We call this a low separation rank representation, and I can explain why in a second. But basically, we're instead of having a different G for every term, everyone has to use the same G. For tractability, we can also make these things have orthonormal columns or something like, if we need to kind of enforce all of the stuff into G, and everybody has to kind of share the same basis. So that's the low separation rank structure. So it looks like this. It's a linear combination, and I think I used something like this in the poster graphic for the talk. So this is where now you see where it is. So why do we call it low separation rank? It's from this paper by Tsiligikaridis and Hiro, which was looking at estimating covariance matrices with this mixture Kronecker product structure. So in our problem, if we vectorize our problem, we can see that actually we're getting this structure in the factor matrices that multiply our core tensor. Our core tensor is the same for all of them. So what we're saying is, oh, it's actually just a mixture of these Kronecker product matrices. And this is exactly the thing they were looking at in the context of structured covariance matrices. Right. So if we look at this spectrum of like more restrictive to less restrictive modeling, on the bottom end we have this CP decomposition. It's very structured, kind of limiting. The Tucker factorization says, okay, I'll fill in all the entries in that was a diagonal core and now make it a dense core. Now we're saying let's take a linear combination but keep the same core, and then this block tensor decomposition up here is very expressive, but has a lot of it's very expressive, but it's not very compact. So we can try to interpret this as a sort of bias variance trade-off in terms of the parameterization. So our observation was that these models work not as well as we would want in problems that we care about, and this is like intractable for problems that we care about. The advantage of this is we can kind of let the representation grow. We can increase the number of terms gradually if we have more data. And so we can choose a number of terms in this combination to fit our problem, depending on the amount of data we have. And in the experiments that we did, like 2 or 3 is actually already significantly better than using just one. So given the time, I guess in the last I will talk about the regression problem and not talk about the dictionary learning problem. But so I want to talk about regression and classification with structured tensors. So this is the original problem that was motivating this. Right. So what we actually look at in this work is generalized linear models. So this means we're not just sticking with the linear regression problem. We're looking at things like linear regression, logistic regression, Poisson regression, basically, any kind of regression problem where where the thing you care about, the way in which the outcome depends on the data is through an inner product. We take some function of the inner product, and to make this more formal, we're actually assuming that the response comes from an exponential distribution, and the parameter of that exponential distribution is actually given by this inner product. This exponential distribution, the randomness here is the noise. So if this was a Gaussian distribution, this would be the inner product plus noise. Right? And so one example is logistic regression, where you say y is actually a Bernoulli. It's a +1 -1 response that depends. The parameter depends on the dot product, but it's random because it's randomly. You get a random label that has that depends on this inner product. So for now, though, I mean, for the purpose of the talk, let's just think about linear regression because it's easier to think about. So there has been prior work using CP and Tucker decompositions for this. We're not inventing the idea of using tensor decompositions in regression. But what we're going to use is low separation rank models for our generalized linear models. So for general regression problems, more general regression problems, and this more flexible modeling that I just talked about. Prior work includes using CP decompositions with logistic regression, CP composition with generalized linear models, Tucker decompositions with linear regression, Tucker decompositions with logistic regression, and Tucker decompositions with generalized linear models. A lot of this work is empirical, purely empirical, and doesn't have any theoretical analysis, but shows the promise. What these works really do is show the promise of restricting the structure, making the structure on the B, the regression vector or regression tensor, putting that structure on can help a lot. It can make the difference between seeing essentially garbage versus actually seeing something good. I guess the main exception I would say to the no theory is that there's actually quite some nice theory in this paper by Zhang et al. From 2020. I think it's in the Cyan Transactions on Data Science. And it uses the Tucker and linear regression. And it's the methods they use there are very tied to the fact that you're doing linear regression. But it's a really nice paper. I recommend it. So, just doing something on synthetic data, we kind of want to get a sense of is what we're doing helping or not. So the claim that I was making is that by using this low separation rank structure, we can scale the number of parameters to the data set size. And we're interested in the low sample regime. So where you don't have so many samples. And if we can, cook up a synthetic data experiment with some Gaussians. And you can see that using no structure, this green line, basically your error is really bad, even with a very large number of samples. So imposing no structure you're not able to solve the problem at all. Imposing the so this whole range is kind of small number of samples, right? And so if you look at the Tucker regression, the TU is for Tucker, it does pretty well, but then actually kind of is unable to take advantage. At some point, it's unable to take advantage of having more data. Whereas we could do the same as this, but at this point we could switch to increasing the number of terms in our low separation rank, and we can actually continue to improve. So the point is we get that flexibility by being able to say, well, now we have enough data, let's add another term, and we can get more explainability out of the model. So under this low separation rank model, we're looking at the parameter, this B, as having this low separation rank structure. And if we vectorize, then it just turns into a regular regression problem in which the parameter now has this factorization structure that is it's some unknown G multiplied by this sum of these matrices with this Kronecker product structure. So the total number of parameters we have to fit is pretty small. And now we can sort of use techniques that we know about understanding vectors to at least analyze this problem. Right. So some challenges that appear from the math perspective is that we look at the set of all low separation rank tensors with a given number of terms and a given sizes, actually. We have to optimize over this space. This space is not convex. It's kind of weird looking. This also happens just with regular tensors, that you can have a sequence of tensors with this given rank whose limit point is a tensor of higher rank. So like the space of tensors with a given rank is not closed. So that's annoying. So you run into, if you're trying to do optimization and make guarantees over these spaces, you have to either make some more assumptions that your problem is nice, or you have to be very careful about taking some closures and stuff like that. So it's that's the math for that. Since we're a math crowd here, that's the math issue that's going on. The topological properties of this set are not friendly. But if we think from the statistics point of view, it's like, well, let's do the maximum likelihood. Everybody loves maximum likelihood. I hope you love maximum likelihood. So we can actually write down what the we can write down the optimization for the maximum likelihood, and then we can try to maximize the likelihood. And then you look at that problem, it looks very ugly. I put this up here to be like, why are you here? I'm lunch, I want lunch, But what you can do is you can actually just write this as an alternating minimization method where you just minimize over each of the factors one by one, and then and just cycle through. And this actually ends up working quite well. I'm not confident in saying we have a proof of convergence or convergence rates yet, but it looks promising. I just say it looks promising. We're getting there. But so hopefully we'll get there. But from a practical standpoint, you can certainly use this alternating minimization. In particular, what you want to do is use projected gradient descent for each of these terms. Why projected? Because we're insisting that each of these have orthonormal columns. So we take a gradient stamp, we're going to leave that space, and we have to project back on to a set of orthonormal matrices. And then you can just use regular gradient descent on the G. Yeah. So for each, so good question, and I forgot to sort of make this explicit. Each of these subproblems is convex, which is why we should be able to prove something. So it's convex if I fix all of the other factors and only look at one. The problem in linear regression, the problem is like linear. In general, it's going to be convex for these generalized linear. So that makes things nice. Or hopefully nicer. So we did some experiments, and I would like to preface all of the experimental evidence. This is not me saying we have state-of-the-art results on these data sets. This is me saying there seems to be something interesting here, and maybe there's some we're actually taking advantage of something here. So we looked at two real data sets. I had mentioned this ADHD data set before, but there's also another data set on fMRI on autism. And then there's a data set on magnetic resonance angiography. So that's vessel MNIST 3D. So you can see from for those who have done any machine learning, you can see from the MNIST, has nothing to do with digits though. It, in fact, has nothing to do with NIST, but it is a benchmark. It was created as a benchmark data set for trying to understand 3D imaging data. So we looked at a bunch of different algorithms that have been proposed. Many of them, so some of them use different approaches than alternating minimization. So there's a optimization method for fitting Tucker plus GLM. There's Tucker plus logistic regression, and completely unstructured logistic regression, which is just regular logistic regression, and then also the CP. So we look at the autism data. Okay, now you'll be like, no, you lied to us. You're not going to say our results are the best. I can say, aha, our result is the best. See the yellow box. We're the best. But But again, I want you to take this with a grain of salt. It's more to say that imposing the kind of structure that we have lets us take better advantage, we think, of the amount of data that we have than more limited models or no modeling. So we're kind of trying to be somewhere between no structure and too much structure. And so we feel like we're getting somewhere in between there. And here, I'd like to emphasize also that, you know, there's a problem which I haven't said how to solve, like how do you choose the sizes of the ranks in your model and all this other stuff that is, I'm going to say, a problem for someone else. So we tried this, it seemed to work, and this is but we only needed 2 terms in our LSR decomposition. So it's only 2 terms, and we're doing pretty well. The 2 things to note here are the things that I mentioned before, that the unstructured models, that is just looking at support vector machines or logistic regressions, they're really bad in this if you don't have enough data, which is not surprising. And the other thing is the thing I just said, where if I just add one more Tucker term to my representation, I can get advantages. Seem to be able to get advantages. On the MNIST data set, we also looked at because it was an MNIST data set. Somebody had already done some work training a neural network, so we tried to compare it against a neural network. And so here, we can say, we win, we get better accuracy. But if you look at sort of how the errors are distributed, this question, this story is a little bit more mixed. But again, we only needed two factors, and we didn't need to optimize a gigantic neural network. And so if you want to, we have a paper, I can give you the reference, or you can find it pretty easily, where we kind of discuss this a bit further. And again, issues such as, what is the overfitting of this? What are the overfitting properties of these looking at interpretability? One advantage of using structured models like classical statistical models is that they allow for more interpretation of the parameters, which regions of the brain are more important and that sort of thing than sort of neural network will be able to do. And so I think there's a lot of interesting work on the empirical side, and also perhaps on the theoretical side, maybe a blend of these 2 approaches would work. Okay, so that's empirical. So what about the theory? So we can show right now, I mean, what we have, sort of proved, fully is a lower bound, where we can say if your data was generated from a tensor with low separation rank, then you need a certain number of samples. You'll need a minimum number of samples in order to recover that original tensor. And this, the thing to note here is that the number of samples you need is linear in the number of free variables, the number of parameters in the model, which is the thing that you would want. And so this result actually generalizes the existing lower bounds. So this is an information theoretic lower bound, as they like to say in statistics. Just means it used Fano's inequality. So, we can, but this will recover the existing results. And so there's a table in the paper, which I pasted here. So kind of comparing what we get, and we can sort of fill in bits of the table, which we didn't know before, and they will specialize to these different cases. All right. So what do we want to do next in this direction? So I will say I made these slides before maybe like the end of the semester, and over the summer some more stuff has happened. So this is the state of things before. So we do, I think now we have to submit the paper, but we have conditions under which we can say that the maximum likelihood estimate is consistent in a local sense. That is, if you start from locally, you'll be able to close enough to the solution, then you'll be able to identify the true parameter. I think the math question I mentioned before, all the topological issues, I think are really interesting, and there's like not sufficiently understood. So there's some stuff to do there, I think. And we have an approach for doing the convergence analysis for the alternating minimization, but it's at the level of using this idea and this idea and this idea, we should be able to show something. there doesn't seem to be anything on the face of it that will prevent us, but we haven't done it. So, and if there's anything I learned in grad school is like you go in very optimistic, and then you realize that there's something that you missed. And so I'm waiting for the other shoe to drop, as they say, and on this one. Last little thing, in terms of applications. So this is what the undergraduate did last summer, is he tried to do this in a federated learning setting. Some folks learned what federated learning is this earlier today. But in federated learning, the idea is you have many sites which say, for example, all have MRI data, and they'd like to collaborate to learn this regression model. And so they'll do that by using a coordinator who can collect some updates from them to update this B tensor and send back the results. The advantage of the factorization structure is the amount of data that needs to be transmitted is smaller, and the actual MRIs get to stay at their local sites. So that's the you can do. And it turns out that one disadvantage maybe of our alternating minimization approach is that you need very tight coupling between the iterations. So you can't let the local sites do a lot of processing and then sync up. You need to kind of be very tightly tightly connected. So in particular, if you don't sync up, you can get like a non-convergence if you like empirically for this. So still investigating this. I think there's a lot of interesting work in terms of the engineering for this problem. Okay, so I'm going to skip this. Houses, very good. Okay, great. So again, my central thesis is that there's a whole continuum of these tensor decompositions, and this low separation rank one that we've been working with, I would like to argue, can be very useful. It allows us to adapt the parameterization to the data available, and we can efficiently, at least in a computational sense, estimate, we can fit these models effectively. It doesn't take a ton of time. But again, there's lots of mathematical questions. One is, I also think in terms of like open questions, is an approximation result. So if I give you a tensor with low separation rank structure and I add a little bit of noise to it, how do I denoise it? How do I project back onto the set of low separation rank tensors? And does that actually reduce the amount of noise? Does that actually does that reduce the error or not? We don't know. So great problem for those who want to do some approximation type results. The topology problems that I mentioned before. And then there's also interesting questions in optimization theory. A popular way of handling non-convex problems is to do a convex relaxation of the problem and then hope for the best, and then prove some theorems that suggest that what you did was not a bad idea. We don't really know the right way to do a convex relaxation of this particular constraint. We have a proposal, but we don't know if it's a good idea or not. So there's some theory that can be done there. And then also, like we know a lot about random matrices and their properties. We don't know that much about random tensors except for empirically. So there's work, for example, if I generate a random tensor, what is its CP rank? That kind of thing. We don't have like a good sense of that. We don't know, which would kind of asking what is the spectral, kind of asking questions about the spectrum of a random matrix. We don't know too much about the spectrum of a random tensor. So, and then specifically, if I have simpler structure, what can I say about those? We don't know much about that. I think that's super interesting to think about from a math perspective, and somebody who wants to do math would be great to do. So thank you very much for your attention. And
right, thanks a lot for the talk. Any questions from the audience? We have people also on Zoom, so maybe we'll start with them. Yes, Danny.
Yeah, stress tensors.
Now, beyond this, you mentioned something very interesting for me, and I think the hyperfactor imaging. So, from what I understand, is that you are coming up with a new way to represent much information to maintain patient.
Yeah.
But the hyperfactor, they are really sort of really, tensor. So, have you seen any works with machine learning or computer vision where the representation to adopt it, useful and have improved results beyond just like looking at vectorization.
Yeah, so at least, I mean, from an empirical standpoint, there is work in computer vision. There's a work by actually a friend of mine, Tamir Hazan, with his advisor Amnon Shashua, which is from, I want to say, early 2000s or mid 2000s, which uses this in the computer vision context as a CVPR paper, that kind of computer vision thing where they look at tensor decompositions and show improvements in certain computer vision tasks. For hyperspectral imaging, I've seen one or two works using tensor factorizations in a way that my student found very hard to understand. And so it does not seem like it seemed a little, to my mind, ad hoc when I was looking at it. And I think like taking a kind of first principle approach to this, and that's something that I would be, I'm interested in thinking about, but I need to learn more myself about, the physics of hyperspectral imaging to kind of, I think, come up with something good. Like the way that N members are used and stuff like that is different in different applications. But there is some work, I think, in the IEEE transactions on geosensing, whatever it's called, the GRSS journal. Yeah. I should maybe able to dig up some references if you email. Yeah.
Other questions? Yes, go ahead.
You mentioned that the number of terms in this decomposition for number of mixtures is somehow related to the number of observations, but there is no like.
Yeah, we don't have I mean, except in order-wise sense, we don't have and the thing is, whenever you get these sort of theoretical order-wise results, then when you try to map them into a particular problem like hyperspectral imaging or medical imaging, then you don't know what the constants are. So you just kind of like, sure, it's 1,000 times this thing, and then this other application is 10 times this thing. So we don't really, and this model order selection or selecting the complexity of the model isn't endemic to many problems. And so I don't know if I would say it's worse here, but it's certainly as bad as it is in any other problem where you need to pick the size of the parameterization or the size of the neural network or the number of layers in the neural network, all this stuff as well. It's very hand-wavy.
I don't know, then at some point, probably you mentioned like 2 terms are enough, or 5 or 6 terms.
Yeah, in the experiments we did, we saw that 2, for the amount of data that we had, 2 was significantly better than 1. And the other hard thing is that we don't have, this is, I would say, speculative in that way that a lot of information theory is also speculative, that we don't actually have data sets. We can construct synthetic data sets, but we don't really have enough data at the moment to validate and decide, oh, well, actually you want 5 maybe for this one. So yeah, definitely an issue.
Salim?
Yeah, following up on the question about the prioritization. When you say something about informational capacity, like solving the problem as a factor, or just solving it.
Oh, so yeah, I mean, because if you just ignore all the structure and vectorize, the complexity is then going to be dictated by the number of parameters, which is, in a sense, like exponent. It's a product of terms versus a sum, so you get this kind of blow up there. I think I haven't looked at the scaling. There's a little bit of I guess, okay, again, thinking if I put my information theory hat on, I guess I should put my information theory hat on all the time since they're paying for me to come here, partly, at least. So they, if, what you might want to consider for that is like, if I have a sequence of growing problems of growing size, but then your data is increasing in dimension. So it's kind of usually, when you really, from a statistics point of view, you want to think of the data set dimension as fixed and you're increasing the number of samples. But to answer this kind of complexity scaling, you'd be thinking about a sequence of problems where the tensors are getting bigger and bigger. Now, that is not necessarily crazy to think about, because you could instead think about, I have a fixed area and I'm going to sample more and more densely. But then what you want to do is, I have a continuous phenomenon. I'm going to sample it at discrete points. I'm going to measure the spectrum in the hyperspectral image at these points. Now, what if I had a higher resolution imaging system? How, as I increase the resolution capability of that imaging system, will I be better able to reconstruct some original tensor structure? But I don't know how to do the continuous version of this. That'd be very cool to think about.
Thanks. Any questions from Zoom? If you have questions, please feel free to unmute yourself and ask. Maybe
Is anyone on Zoom?
Yes. Yes, Brahim.
So this lower bound, so big on the number of samples that aspire to the Frobenius norm.
Yes, yeah, so the Frobenius.
So is there any hope getting this bound or some bound if I do a different norm?
Oh, if you do a different norm. I have to think about it.
I'm just curious about the methodology.
Oh, so we have to do we have to construct a packing in the space of low separation rank tensors. So we have a particular construction. And for that, we can calculate the Frobenius norm. If you wanted to use a different norm, we might need a different construction.
It's not straightforward.
It depends on the norm you want to choose. If it's an LP norm, I feel like more confident saying we can do something. If it's some other weird norm, then I don't know.
The reason I'm asking is that those in the context of regression, right? So those inner products are tied to
Frobenius.
L2.
Yeah, L2, right.
So if you want to do something other than right, something like I don't know, also you can think about it as neural averaging, right? So it's kind of a geometric average, summation of two inside. What do you want to do? What do you want to do geometry? This seems, at least in the context of whenever you have data, heavy tails,
right?
Or even linear regression, you wouldn't want to choose it. I mean, you wouldn't want to choose L2 norms.
Right.
Like that.
Yeah. I think there's two. Well, I have two completely different thoughts. One is, we are considering generalized linear regression. So it's tied to L2, but everything is tied through the link function. So the recovery is in L2, but the way in which the response, the distribution of the Y depends on, that distribution could be heavy tailed, but parameterized by potential, well, I don't know, heavy tail's not in the exponential family, maybe. Are they? Are alpha stable distributions the exponential family? No.
No.
No, right, it's not. So, right. So I thought not. So, you could get maybe not heavy tail, but you could certainly expand the scope of distributions you can handle. So that's one non-answer to your question. And another non-answer to your question is that I think, yeah, you'd have to sort of reformulate the problem from scratch. That being said, at least for the lower bounds, I think you can still do constructions and try to show things, because the constructions are geometric, more or less. I mean, the analysis is about the geometry and less about the probability part of it. I mean, you do need to calculate some mutual informations, but maybe you can adopt a different strategy for heavy tail phenomena and stuff like that. Yeah.
All right. Thank you so much.
Yeah.
So I should wrap up, and let's have the speaker again, and thank you all for coming.
Microphone.